Okay, so I promised that I would do some more on theta, and what I did is took some notes. I'm going to start talking about consensus. So I pulled some relevant information out of the white paper. There are two white papers that are important now. It's the second one and the third one. The second one goes through a lot of the things, basic type things. The the third one goes on to the changes that are coming out in the third version of Theta. So we're going to talk today about consensus, and it's described as multi-level Byzantine fault tolerance. That's based on the Byzantine generals problem, which is a way of producing the correct consensus as long as a large percentage or a certain percent. I think in Bitcoin it's over 50%, or it's either 50% or 2/3. Provide the correct information. So you can have a large number of nodes presenting poor information, and it can still come up with the correct solution. And the validator committee is essentially the people who the nodes that produce blocks as quickly as possible. Remember, with theta, the key thing is speed, right? Because you're moving video, and they use what they call a practical Byzantine fault tolerance consensus algorithm. I'm not going to get into it too much today, although I think it's worthy of its own separate video. It's solve a lot of the problems with the traditional Byzantine fault tolerance algorithm, and it's designed to be fast. So if you have enough validators, you can create blocks really quickly. And then you have the guardians. They're the ones who finalize the chain, and they define that as having more than 2/3 of the guardians seeing the same thing, same chain of blocks. The nice thing is the way they speed it up is they only need to agree on a hashtag of what they call checkpoint blocks. So basically taking a sample. So so you have, let's say t equals 100, some height. Not clear what height means in this case, but basically they take a sample of the blocks, and if they agree on those, the hash of those, and remember, if a hash is designed correctly, every unique item is going to have a unique hash, with minimum collision. Collision being when two items that are different hash to the same value. So a checkpoint block is similar to the commit step. So again, we're not going to get too much into the commit step of PBFT. Not going to get in too much of that today, but it's already been, the checkpoint block has been signed by the validator, so it's more likely that all the honest guardians have the same value. The only thing left is to have a protocol for the honest guardians to confirm that indeed more than 2/3 of the guardians have the same value, and they call this aggregated signature gossip, or what they propose. Each guardian node keeps combining partially aggregated signatures with its neighbors, and then they gossip about the aggregated signature. So essentially, the the guardian nodes trade information and kind of compare, I guess compare notes would be a good way. Let's see. Then, along with the compact bitmap, which encodes a list of signage. So you have the validated committee against a small set of validated nodes, 10 to 20, and it could be an election, it could be rotating, it could be randomized, depending on how they decide to do it. And these nodes are a certain amount of stake, so there's a certain amount of proof of stake here. And again, if they do something wrong, it can be slashed. And we saw that in Polkadot. And when a consensus is reached on those blocks, they are called settled blocks. So, and the guardian pool is the superset. So the pools contain a large number of nodes, and if they're going to say here, it could be 1,000. And again, there's a certain amount of stake. They can instantly become a guardian. So allowing a lot of participation again provides more security. So what we're dealing with here is essentially multiple levels of security. This is very similar if you've ever done anything with network security, right? You where they talk about multiple layers of security. So you may have something to check on the edge of your network. You might have something like a tripwire to see if, check on if things have been changed maliciously. Virus scanners, different mechanisms that you combine together, even including, it could be something like keeping the key servers in a secure location. So it could be like your house security, right? You can have a video doorbell and cameras outside, and then maybe you have an alarm. Obviously you have locks, and you can have multiple locks. You can have the privacy lock, as I've heard it called, the one that you stick that's in the doorknob, and then maybe you have a lock, a deadbolt lock that is on a separate key. Or you can, various ways of doing that. You can have an alarm system. Some of the older systems, I don't think they do this with the newer ones. The one we had growing up, in my house growing up, actually had an alarm on certain rooms where if a thief got in, they'd want to go because that's where they would assume the desirable items were, like the bedroom and things of that nature. I haven't seen that done in more modern systems, but similar type of thing. Various levels of security, and that's what they're trying to do here. Now, when you look at the docs, they talk about edge nodes, and we will have to get into those in a future video. But I think we do need to discuss this Byzantine fault tolerance, the practical Byzantine fault tolerance, and get into that a little bit more. And again, we talked about guardians, validators, and we did not talk about edge nodes, so we will have to talk about that a little bit too. So this is the start of a series of videos, and again, this comes directly from, I think this is, from the this white paper here, which is this is from 2 years ago. This is their second white paper. And they have a new one that covers the newer level 3 version, and we will get into that. So, okay, hopefully this has been helpful. I think understanding the basis of it, and there are some interesting things that they're doing in terms of security and in terms of speed. They're trying to do security in a way, and validation and consensus in a way that will allow for secure communication, not secure, quick communications. Already doing security, but again, we're doing video, we're doing a lot of data. Whatever methods they use have got to be fast, because they cannot get away with the speed that Bitcoin or Ethereum can get away with. So anyway, hopefully this has been helpful. If it has, please give it a like, and please subscribe and ring the bell to get notified of future videos. So take care, and I will speak to you tomorrow.